Welcome back everyone to section number 3. In this video we're going to be talking about increasing, decreasing, and this thing called concavity. So the claim is we'll be able to utilize the derivative to determine when a function is increasing or decreasing. And then we're going to examine this thing, the second derivative, right? We brought this up once before. We know it's a fun thing to calculate, but what does it actually give us? So in terms of a graph of a function, this will determine the concavity. So concave up or concave down. All right, so like it mentions here, right, we are now kind of embarking on this journey. Our goal is to be able to find detailed sketches, or at least fairly detailed sketches, of functions using their derivatives and derivative information. So that's kind of the goal of this, using derivatives in order to tell something about graphs. Okay, the first theorem I have here is that it says if the derivative is positive on some interval, then the function there is increasing on that interval. Which makes a lot of sense because remember, derivative is slope. So this is essentially saying if you have a positive slope, your function is increasing. And then it's like, yeah, certainly. If your derivative is negative, or if your slope is negative, then the function is decreasing on that interval. All right, let's do a little mini example here. Find where the function is increasing. So I'm going to go ahead and take the derivative, right, because I need something about the f prime. So f prime of x is equal to 2x plus 4. And now we want to solve the inequality. Where is this? Well, we're looking for increasing, so we want it to be greater than 0. So where is 2x plus 4 greater than 0? And I know that we could certainly rearrange this and solve when x is greater than 0 using kind of a more standard method in this case, but I'm going to use the method that we brought up in the previous video in our inequality review because that's more kind of extendable or expandable to more problems. So I'm going to go ahead and first of all figure out when this is undefined or when it is equal to 0. So it's never undefined. I'm going to try to figure out when it's equal to 0. And so that's going to be when 2x is equal to negative 4 or x is equal to negative 2. I'm going to plot this on a number line here. So negative 2, that breaks up the number line into a couple pieces, and then I'm going to choose test values. So maybe in this one I'm going to choose 0. 0 is certainly a number that's bigger than 2. And then down here I'm going to choose negative 3. And I'm going to plug those into my derivative function, right? So this is something about the derivative to figure out if the derivative is positive or negative at these places. So if I plug in negative 3, I'm going to have, let's see, negative 6 plus 4, and that's going to be negative 2, and the big thing that it's less than 0. So over here we have negative. And if I plug in something like 0, well, I'm going to have 0 plus 4, that's going to be 4, and the big thing is that this is greater than 0, so over here I'm going to have positive. And so in this case, our answer was, well, from negative 2 and beyond, all the way up to positive infinity, our function is increasing. So I promised you guys in our last kind of our inequality review video that we were going to be solving lots of inequalities, and now you can kind of see where these things are coming from, right? You're just taking the derivative and figuring out when it's positive or when it's negative. And again, of course, in this one we do have an easier way to go about this. We can just rearrange this like so. X is greater than negative 2, but the claim is that we can only do this in a handful of situations, that this will not really expand to a lot of other problems. This method, though, right here, will expand to a lot of other problems. So this is the one that we kind of want practice with. Okay, so that's a little bit about increasing and decreasing. Moving on, if a graph f lies above all of its tangents on some interval, well, we'll see what this looks like in just a second, but this is what we're defining to be concave up on that interval. Likewise, if the graph f lies below its tangents on some interval, then it is called concave down. So I kind of want to show you what these things look like. So first of all, let's go ahead and sketch maybe this one right here. If you go ahead and you draw a bunch of tangent lines, so here's a tangent line, here's a tangent line, here's one, notice that everywhere on this interval, this function right here seems to lie above its tangent lines. The blue thing seems to be above all of these green lines. So this right here is called concave up, because the function lies above its tangent lines. Likewise, if you have something like this, let me try one more here. Yeah, something like that, and you go ahead and you draw the tangent lines. Oops, something like this, something like this. Again, you can see the blue line lies above all these green tangent lines. So again, this is concave up. Now concave down, again, this is where the function lies below its tangent line. So if I go ahead and I draw something like this, draw in a few tangent lines, you can see on this entire interval, it lies below its tangent line, so therefore this one is concave down. And now finally, maybe something, I'll give myself one more shot here. There we go, that's better. This right here is also concave down. It lies below its tangent lines. Something like this. So those are both concave down. And I want to bring up something kind of important here. It's easy when you start doing problems. A common mistake that I see is that people kind of confuse concavity with increasing, decreasing. So I want to mention that this right here is increasing, which I'll just denote with ink. This one right here is decreasing. Likewise, this one right here is increasing, right? It's going up. And this one right here is decreasing. It's going down. So concavity and increasing, decreasing, right, which is something that we just brought up here, concavity and increasing, decreasing are two separate topics. Just because you have something's increasing doesn't mean it's necessarily concave up, right? Because there's increasing over here and they happen to be concave down. Likewise, just because you have something is concave up doesn't mean that it's increasing, right? Here's a case where it's concave up and yet decreasing. So these are completely separate. You kind of have to hold them in two different hands, right? You need to make sure that just because you have one, it doesn't really imply the other in any way. Okay, so how can we tell if a graph is concave up or concave down? Well, the claim is this has something to do with the second derivative. So if the second derivative is greater than 0 for all x in some interval, then the graph of f is concave upward on that interval, or concave up. Likewise, if the second derivative is less than 0 for all x in an interval, then it is concave downward, or concave down on that interval. So now we have a concavity test. So I have one more problem for us here. Find where this function is concave up. So again, concavity has something to do with the second derivative. So I'm going to go ahead and find the second derivative. 2x plus 4, and take one more derivative here, and I'm going to get just 2. And I want to know, when is 2 greater than 0? Well, in this case, when is 2 greater than 0, there are no more x's left. So the claim is this is always greater than 0, so therefore it's always concave up. So we're going to say in all real numbers, or that's going to be from negative infinity all the way to infinity, this thing is concave up. And now just to verify what this means, I went ahead and I graphed it for us here. Oops, there we are. And so I have my function, x squared plus 4x plus 5, and I went ahead and I drew the tangent line. So the tangent line is blue in this case. And notice that this red parabola, our function, always lies above the tangent line, right? It always is above the tangent line. So therefore, no matter what value you have here, it is always concave up. All right, that should do it for us in this video. This is a nice introduction to increasing, decreasing, concave up, concave down. Next time we're going to be talking about these things in order to find local mins and maxes, as this next title suggests. I'll see you then.